This is the simplest way to turn voice to text, transcribe automatically with Python and Hugging Face. We're going to use PyTorch and the Hugging Face library to automatically download a model and use it to transcribe an audio file. So let's start off by importing Torch audio, and from Hugging Face transformers, importing wave2vec2 for CTC and the wave2vec2 processor. These two will help us get it done. Now let's initialize the model with the let's initialize the model with the wave2vec for CTC and obtain it by using the from pre-trained function. And in this case, what I'm going to do is I'm going to use the default this large model from the Hugging Face hub that can get the job done. And we're going to initialize the processor as well. The processor is going to be used to process the audio file into tensors that the model can consume. So both have been initialized now. Let's take a look. It's a good idea to look at the model to inspect what the model is, and what we can see is that it's a wave2vec2 for CTC class model, and these are different NN layers. And let's also take a good look at the model.config object. And the last thing that we'll inspect is the processor object, the processor class. So this includes the wave2vec2 feature extractor and the tokenizer, and it's important to take note of the sampling rate. The sampling rate of this processor is at 16,000, so we'll save it as a sampling rate variable from the feature extractor. Now this is important because not all audio files are sampled at this frequency, but matching the frequency is important to get the best prediction. Now this is just a little bit of boilerplate to import the audio file. I like using the OS module because this way I can use the same writing style, whether it's Mac OS X or Windows computer. It's the forward and backslashes are just the same. So we're gonna get the audio wave path, and this is a simple audio wave that is downloaded from a Kaggle dataset. Now we're going to use Torch audio to load that into memory, into a tensor actually. So torch audio.load path to wave. Now if we inspect this file, we see that it returns a tuple. One is a torch tensor that includes the audio data, and the second item in the tuple is the actual sampling rate of the file, and as we see, it's not the same as what the model expects, so we will need to resample it. So first of all, let's decouple our tuple. I'll use the PT tensor as the tensor and SR as the sampling rate of this file, and it's 48,000, whereas the model expects 16,000. So now we'll be resampling it. To resample it, Torch Audio actually provides a convenience feature that can be accessed through torchaudio.functional.resample, and this is going to require the tensor, the original frequency, and the new required frequency, and we have all of those handy, so we'll be able to insert them. Original frequency being SR, and the new frequency, what we need being 16,000, which is saved as sampling rate. So let's run this. And now let's just see what the resampled tensor looks like. As you'll see, this is not a tuple, so the sampling rate information is not in this. It's simply the tensor with the audio information. And now we'll be able to pass this tensor into our processor that expects a sampling rate of 16,000. So let's pass it into the processor as resampled, and let's pass the sampling rate as well. This is simply to confirm that we have resampled it. And let's pass the return tensors as PT, because we can get TensorFlow, we can get NumPy arrays as a return tensor, or PyTorch tensors if we're working with PyTorch. And so we got our process tensor. Let's see what it looks like. So first of all, we got input values, but as you see here, this is a NumPy array, and we're expecting PyTorch tensors because we're dealing with a PyTorch model. So where did we go wrong? Oh yes, actually we have to put return tensors with an S, and now if we run it again, we get PyTorch tensors that are returned with an attention mask. So processed tensor.input values will give the audio data tensor as expected. And let's see if we can pass this directly into the model out, and pass the processed tensor in there and see what comes out of it and how we can deal with that. And as you see here, we get an error. And basically what the error says is that the tensor size does not match. Then we're going to back up a little bit and look into it again. We're going to look at the process tensor's input value, and we're going to inspect the shape of this tensor. And what we realize is that there's the batch information at the first index, but a channel information at the second index. And well, this is a mono-channel recording, so there's only one channel. But this screws up the model because the model actually only expects single channel tensors, so it doesn't even require the channel index because it expects it to be a single channel. So all we have to do now is take that input values tensor and squeeze it at the index of 1 to eliminate that channel index, and now we have batch and the tensor with the audio information. So we should be good to pass this on into the model and see what we get out of it. So model out is equal to model new process tensor, and let's see what this output looks like. And there you have it. So you get a model output that includes a loss. Here is none because we didn't actually enter the target values, and the logits, which is a tensor. You also get well, hidden states and attention, that is none. And let's take a look at the model logits and the shape of it. And here we see that it's a tensor of size of batch size 1, and with 33 and 33 at index 2 and 3. And what this is in reality is the number of predicted characters as well as the vocabulary size of the processor. So if we take the argmax of the vocabulary, we get the most likely predicted token at each index. So then that should return the maximum likelihood value at the 33 positions, which the processor can then decode. And there you have it. You've transcribed audio into text. Like and subscribe if you like this and want to see more.